Last class, we looked at the fundamental concepts of stability analysis in the frequency domain that you would have learned in a linear control system course. Since some of you hadn't taken a control system course, I did a little bit of a deep dive into it. So let's just quickly review what we learned last week and try to apply that for this lecture so that we can control the DC motor. So this is our equation for a DC motor. Going forward, I'll put it in the transfer function form because this is the form we are going to be using to design the control system. So we have the four set of equations that you have seen before. And we are going to be looking at, so when I say an open loop transfer function, for example, let's say I want to control the current in the motor. Let's say somehow the EMF has been made zero by basically holding the rotor tight so that it doesn't rotate, EMF is zero. Then the open loop transfer function basically gives a relationship between for a given voltage, what will be the current, right? How the current would respond for any given voltage that is given by this transfer function 1 by SL plus R. And that is what we are going to be calling open loop transfer function, right? And the closed loop transfer function will be once you put this in some kind of control loop and close the whole loop, what it comes out to be. Typically, it will not just be a plant, it will also be another controller. In case of PA controller, will have its own transfer function. The combined transfer function of the plant P of S and the controller transfer function, say PI of S, that whole combined system would be the G of S open loop transfer function in that case, right? And then once you have the open loop transfer function, we figure out how to get the closed loop transfer function. For this lecture, I'm gonna, some places I put H of S, some places I use the H of S term. That is somewhat intentional. We are going to assume H of S is 1 for simplicity. Even if we have some kind of sensor with some sensor gain, that can be quite easily modeled. But all the analysis that I've done there, wherever I say G of S, it's for G of S, H of S. I've just dropped the H of S term, assuming it's 1, right? Okay. So we are going to be interested only in systems which are going to be closed loop stable, right? If you have a system and if you're going to make the system unstable, that's of no use to us. So we're only interested in closed loop stable. That means that there should be no right-hand side poles to the solution for the root of the characteristic equation of the denominator of C of S. So C of S has some form. Let's say C of S is some numerator of S divided by some denominator of S. And the denominator of S, that when you equate it to 0 and solve for the roots, typically in our case, it'll just be a quadratic equation, so pretty straightforward. So when you solve for the roots, none of those roots, real parts should have any positive component. They should all be negative real parts. If they had positive parts, then you will have e power alpha t, alpha being positive. That means you have exponentially increasing signal. For a bounded input, you'll have unbounded output, which means it's completely unstable, right? So this is the first requirement that we have for closed loop system to be stable. The denominator of C of S must be all on the left-hand side, the solution for the root. That also means the zeros are the solution to the numerator, right? So this is the denominator of C of S. And this result can be represented as some numerator of S divided by some denominator of S. Let me call it some prime, right, which is different from this. And if the denominator of C of S must be 0, that will be same as the numerator of 1 plus G of S H of S, right? So none of those must have any zeros if the D of S should not have any poles on the RHS, which is one and the same. So these two statements are exactly the same. So for this particular system where the system becomes stable, we saw what is going to happen to the Nyquist plot. So how do we get the Nyquist plot? We basically take a full loop, covering a whole RHS plane. So we start from 0, go all the way to negative infinity, from negative infinity, go to all the way to positive infinity, and that we can represent by R e power j theta with R tending towards infinity. That will cover the full RHS plane. And then from infinity come back to 0, we have created an anti-clockwise going loop, right? And when we map every single point, so we take this point, this point, this point, this point, every single point onto an equivalent point on this curve. Depending on the equation, it can lie anywhere, okay? And if we look at how many times this curve in the f of s plane encircles the origin, it should be equal to, encloses the origin in the counterclockwise direction. It should be exactly equal to the number of poles of G of S that are on the RHS plane, right? G of S can have poles on the RHS plane. The open loop system can be completely unstable. That is not bothering us at all. It's the closed loop system that should not be unstable. All right. So just because I put poles here, that doesn't mean C of S is unstable, because this is not the poles of C of S, right? This is the poles of G of S. So open loop system can have poles on the RHS. As long as the open loop system does not have zeros on the RHS, our closed loop system would also not have poles on the RHS. That will make the system stable. So whatever I've drawn here is a completely stable system. So this is for G of S, right? So it has poles on the RHS, but it has no zeros on the RHS. So, And then once we go to the Nyquist domain, in the frequency domain and map each of those single points, we see that it will encircle the origin in the anti-clockwise direction. And the number of times it encircles must be exactly equal to the number of poles we identified here. Even if it's one less, that means a zero has snuck in here. Right? That will be problematic because the system is now unstable. What did you have a question?
So what if there is a pole like right on the imaginary axis?
That is a little bit of a complicated picture. So let's say you had a pole in this cable. You would get, so an example of this would be a DC network with an LC circuit, right? You've given bounded input. Your output is going to be, if you look at what your current is, if you give a DC voltage to your LC circuit and look at what the current is, it's going to be purely oscillatory. So there are two conditions for stability, for strict stability. One is that for a bounded input, the output must be bounded, which it satisfies. And the other thing is for impulse input, the output must converge to zero. All right, that won't happen for this. If you give an impulse voltage, there is not, and then you say you give a tiny amount of voltage and short this out. This is basically a tank circuit, right? The energy is going to oscillate between the capacitor, inductor, capacitor, inductor, capacitor, inductor. So the current for that, if you give an impulse voltage, would look like this, right? So instead of a DC voltage, I give a pulse and then turn it off. There is going to be a current which goes on and off, right? It is bounded. There is an upper limit and a lower limit for the signal. So it satisfies one condition for stability, but it doesn't satisfy the other condition for strict stability, which is that for a bounded input, you would expect an output that would converge to zero, right? So it doesn't satisfy that. So whether you want to call it stable or unstable, that's totally up to you, but it's not strict stable, but it's stable, right? So that's what would happen if you had poles on the top and the bottom, right? Any questions? Yep, John.
So if G of S.
Oh, just a second, before I come. That is if you have one pole. If you have double pole, it will become exponentially large. So there's only for one pole on the G omega axis. If you have a double pole on the G omega axis, it's definitely an unstable system. Right? Yep, John.
So if G of S doesn't have any right-hand plane zeros, even when you add one to it, is that also always true?
Could you repeat that? Sorry.
Like if G of, so like for one plus, or for the closed loop system to be stable, G of S can't have any right-hand plane zeros, right?
No. So for the closed loop system to be stable, 1 plus G of S can't have any right-hand side zeros.
Yeah.
G of S doesn't matter.
Okay.
Right? It's so this term should not have any zeros, right? So this n prime of S is not the same as this n of S.
So adding one can change like the pole to zeros, okay.
Because just a simple example, if you have transfer function 1 by S plus 3, right? So in this case, you have S plus 3, by adding that 1, you get a denominator of S plus 4. So it does shift away the poles. Any questions? Okay. So everybody clear so far? Right? So then we started adding more constraint to the system based on what we have in our real world for our motors. The first thing that we can observe is our system is open loop stable to start off with. We're starting with a completely stable system, so we can restrict our analysis just to that particular case alone. And once we limit our analysis to that, then we come up with this constraint that open loop transfer function has no RHS zeros, RHS poles, sorry. So if I have a system like, so what all would qualify for this? I could have S squared plus 3S plus, I'm assuming 2. Hopefully when you factor out the roots are all on the LHS, right? But if I had something like this is not a correct, it will not be a feasible solution for our system, right? So for these kind of systems where all the poles are on the LHS, then what we can make an observation is that 1 plus G of S, H of S has no poles. That would be these. We already eliminated the zeros. Now we are going to eliminate the poles as well, right? Because what are the poles of 1 plus G of S, H of S? Those are going to be the same as the poles of G of S. Right? So if you had some transfer, let's say G of S was some numerator of S divided by denominator of S. 1 plus G of S is just going to be denominator of S plus numerator of S divided by denominator of S. Right? If you look at the poles for 1 plus G of S, that is the same as the poles for G of S. That doesn't change. Only the numerator part changed out. So if I say the open loop system is stable, that means D of S for the denominator of G of S does not have any poles on the LHS. That also means denominator of 1 plus G of S, H of S does not have any poles on the LHS. Right? So we have previously eliminated zeros. Now we are eliminating so we have previously eliminated this because C of S is stable. Now we are eliminating this because G of S is stable. So given that, then what does it mean from our Nyquist constraint that we would not encircle the origin in any way once we go to the f of s plane, right? Because the number of times we encircle the origin must be equal to the number of poles that are there. If I say there are no poles, then no, then it's not going to enclose the origin at all in any way, right? Everybody clear so far? Okay. So the second constraint that we added is again for our kind of system where the order of the denominator is explicitly larger than the order of the numerator. Right? So this is again, it needs to be larger. You can't have a transfer function like s divided by s plus 2. Right? This would not satisfy this constraint. So if I had a transfer function like this, that would fail this constraint, this transfer function would fail this constraint. Or it's only transfer functions where so I can have this though. Right? Because the order of the denominator is 2, order of the numerator is 1, so that is absolutely fine. So in those cases, what happens is something very nice happens. If I substitute s equal to r e power j theta, right, with r tending to infinity, the numerator term will, the denominator term will blow up faster than the numerator term. So whenever r goes to infinity, the whole transfer function just collapses into a single point, which is just the origin, right? So all these points that are here, this whole curve would just collapse into one single point, which is the origin, right? So that is the advantage of putting this constraint on the system. And once we have this constraint, now let's analyze what the rest of the remaining plots are. So if this half of the curve that I have would just be the g of j omega plot, right? All that remains afterwards, if I cut off this whole thing, because this whole thing just goes to 0, is I just need to analyze this portion and this portion. And what is this portion? This is omega belonging to 0 to negative infinity to 0, right? And this would be omega belonging to 0 and positive infinity. Negative infinity. So I just need to analyze the vertical axis alone, substitute for different values of omega into my g of s function, replace it with j omega, and go sweep the whole range of omegas, and I'll get this curve effectively, right? And then from this curve, we can again observe there is a nice symmetry around it, around the real axis. So when I plot it, I don't need to do the evaluation for omega belonging to negative infinity to 0. All I need to do is evaluate from 0 to infinity, and the rest of the curve will fall into place on its own. Right? So I don't need this portion of the curve at all. Just by looking at this curve, I can visualize, okay, the other one would just be the pure mirror symmetry. Why waste time trying to evaluate it? And now the stability condition, there's one more simplification that I'm going to do. And the question Jonah asked would kind of fit in with this simplification that I'm doing. So when I need to find out the poles or the zeros, for this I need to solve this quadrant, whatever this equation comes out to be, right? d of s plus n of s. And then I have to figure out the roots for it and so on and so forth. This is an unnecessary complication. I can simplify this whole process if I redefine a new plane, m of s, which is f of s minus 1. Right? So what that means is taking this whole f of s plane and just shifting the whole figure left by a value of 1. Right? So I'm just going to subtract away 1, and then m of s is just a transfer function g of s alone. So if I'm given an open loop transfer function, I just need to analyze the roots of the open loop transfer function numerator and the denominator, and I know everything about the stability of the system. I don't need to do 1 plus g of s. I don't need to do g of s divided by 1 plus g of s h of s. None of those complications are necessary. Right? So once I take the g of s plot and then plot g of j omega with further constraint that omega needs to be just between 0 and positive infinity, I get a curve. Let's say I get this red curve, whichever I've drawn here is the same thing that I've drawn here. Right? And now the new condition for stability is previously it shouldn't enclose the origin 0. In this case, it shouldn't enclose negative 1 plus j0. Right? This is the new constraint that we have. Everybody clear so far? All right. This is actually, yeah. So in this case, I've drawn 3 different curves, the same plot. So whatever our transfer function in red is, I've phase shifted it a little bit and drawn the other one, which is the purple, and I've delayed it even further and drawn the green one. Right? From this diagram, which one is stable, which one is unstable, which one is partially stable? What about the red curve? Is it stable? Right? Because it's not enclosing minus 1 plus j0. So if I give you a plot of some transfer function, the Nyquist plot of it, and if I ask you if it's stable, all you have to see if it encloses minus 1 plus j0, it doesn't enclose, so we are good. How about the green one? Okay. So it does enclose, so it becomes unstable. Again, I've only drawn the half of the plot, so you need to complete the other half to figure out stability, how well it comes out to look like. Right? So it does enclose the origin. It would lie on top of the other one. So, and then the purple one would be the point where it's marginally stable or unstable depending on the number of poles that are on the j omega axis. Okay? Everybody clear so far how we can get stability? So the idea that I want to take away from this thing is, if I am given some transfer function that is closed loop stable, and if there is some kind of measurement that's going on in the system that's having some delay in our system, that is basically any time delay that we have here is basically the three curves that I've drawn. More and more time delay that I add into the system, more and more phase lag that becomes in the frequency domain, right? And we will look at that in a little bit more detail when we write down the equations, but that's the overall idea. So if I had to delay the system somehow, such that if I give, what do I mean by delay? I give a sine wave as input to some transfer function g of s, right? And I look at what the output is. So this is our input, and let's say input, and let's say I'm going to draw the output as some green value, right? And let's say the output is some phase delayed by some magnitude, and the magnitude is also reduced by some value. So I'm drawing the output on top of the input. So this is the phase delay that we have. Let's say somehow the system has some mechanism where it's further delaying the signal, right? If it moves it a little bit further out and makes the signal delayed like this, that is effectively saying it's phase shifting the signal output, right? That's effectively this g of s is adding some kind of phase delay to our system. And in a Nyquist plot, that's basically rotating the signal in the other direction, adding more and more phase lag to our system. So what was previously a stable system could become quite unstable if there is too much phase lag in your system. So in theory, you might have designed something very nice, and once you put it in your hardware, it might become quite unstable. There are multiple reasons. You could have done some parameter estimation wrongs or whatever, but quite commonly what the problem would be is that you didn't have sufficient phase margin. I'll get to the term in a second. It's very close to almost becoming unstable. And then you sense you have your ADC signals, you have some kind of filter, which all adds phase delay, right? When you have an RC filter or something, and then your ADC is taking some time to sample it, and your code is taking some time to execute, all of this adding delay in your signal. So you have some input and it is getting phase shifted before it becomes the output because there's a huge amount of delay. And the delay is basically rotating the signal so that in the Nyquist plane, so that it starts to enclose the -1 plus J0, and what was previously stable becomes unstable once you put it in the hardware. Okay. Everybody clear so far? Anybody has any questions? Yep.
So you could only tell about this like hidden instability by doing the Nyquist plot? Like there would be no indication from just evaluating the S-plane?
Oh, we would, if you evaluated the S-plane for the closed loop transfer function, then if you find out the poles for it, then you can quite easily say whether it's stable or unstable. But the advantage of going the Nyquist route is that you don't need to look at the closed loop transfer function at all. Just by looking at the open loop transfer function, I can immediately say whether a system is stable or unstable.
If you just look at the open loop though, like, isn't there some element of the 1 plus G of S, H of S that it wouldn't show you? Like if this was stable, you would still have to check.
No. That is if you don't enclose the -1 plus J0 there, then your C of S would be absolutely stable. Right? Because we chipped away every single part of this and we reduced it in that form. Right? But at no point did we lose any information. We just moved information around. When previously when we had 1 plus G of S, H of S, this was this plot. When I went to this plot, I just subtracted the 1 out.
Okay.
But I also moved the constraint that stability is no longer determined by whether it encloses, this plot, whether it encloses the origin, but now stability is whether it encloses -1 plus J0. Right? So I didn't lose that information of stability being enclosing the origin because when I subtracted this, I moved that stability information also to the other side. Right? And then when I went from the closed loop transfer function, the open loop transfer function to the closed loop transfer function, right? So when I went from this one to this one, here what should have happened in a closed loop transfer function, there should have been no poles on the RHS. Right? But then when I went to the open loop transfer function, I said there should be no zeros on 1 plus G of S, H of S. So I'm taking over the same information that I have here to here. Right? So for my closed loop transfer function to be stable, there should be no poles on the RHS. Which is exactly the same as saying the 1 plus G of S, H of S should have no zeros on the RHS. Right? So if this is satisfied, this is satisfied. Right? And then if this is satisfied, this is satisfied. And then if the last one is satisfied, this is satisfied. So it's all linked back to making C of S stable. Right? At no point did we drop out any information.
So they all imply each other.
Yep, they all imply each other. Any other questions? Yep, sure.
If H of S was like some other value, would it just move that point further to the left?
No. It depends on what H of S is. If H of S was a gain,
Yeah.
I would just stretch the whole aspect of S plane.
Okay.
If it was some other transfer function on its own, that will change the whole curve.
Okay, yeah. But if it's just a constant, like if it were 2, then it would just have to encircle, or you just want to check -2 plus J0?
No, it's always -1 plus J0.
Oh, okay.
It would never, so let's say H of S was, I'll get you in just a second. So let's say here, where were we, G of J omega, H of J omega. What you're asking, would it shift it to -2 plus J0? That would be if you had plus H of J omega.
Okay.
With H being a constant. But that would never happen in the way we have our transfer function. It would never be an added term, it's a multiplicative term.
Okay.
So let's say this was some constant K. Way that would affect this is would make this stretch out the signal in some way. Like, you know, all of these points would become double. So whatever this vector is here, that would get double its length. This one would become double its length. So the curve would look like this. Double, sorry. Okay. So it starts to blow up the curve. It could make our system unstable. So if you have a wrong feedback gain, that can certainly make a system unstable. So let's say we were starting out with the purple curve that I've drawn here. Right, and let's say this -1 plus J0 is somewhere here. Just a little bit farther away. If I had a gain that's twice, then this purple curve would now become look like this. Right? What was previously not enclosing -1 plus J00 can now start to enclose -1 plus J0. So the H of S term is extremely critical. We can't ignore it. Just to make it quite simple, I'm ignoring it, but in reality, you should consider that at all cases. Yep. Oh, just a second, Billy.
Are we assuming that H of S is a proportional gain, or are we assuming that it's just any transfer function?
It can be any transfer function.
Okay, so then how are we able to like simplify the G of S, H of S, and the 1 plus G of S, H of S just to G of S?
Oh, in our case, we are assuming it to be 1.
Okay.
In our case, that's it. We are analyzing just for our case alone, because even when you do the lab experiment, yeah, the H of S would just be a gain factor for us.
Okay.
Right? But in reality, when you do any kind of drive system or something, this will not just be a simple gain. You would have some kind of low pass filter. Because whatever current you measure, voltage you measure, they would carry the switching noises and all of those. You want to filter those out, and they would have their own phase delay and everything. So the H of S is quite critical. We can't ignore it in any way. Right? But factoring for the roots of H of S is very simple though, because it will typically be a low pass filter, which is omega by F plus omega. We already have the root form factored in right there. Right? Yep, Ben.
I was just gonna ask why you're able to do that, but you just said it's unity gain, so.
Yeah, just because, just to keep our discussion simple right now. Right, but otherwise everywhere you would have G of S, H of S. The last plot would also be G of S, H of S. Okay, so once we have this plot, what I have drawn there is basically just an Nyquist plot. Going forward, we don't need to worry about looking at Nyquist plot at all, because whatever I have drawn there, this curve, okay, this was what was the value? This was basically plotting G of J omega for omega belonging to the closed interval 0 to the open interval positive infinity. Okay, so I said, well, how do I get that? Let's say I have some transfer function 1 by S plus 1, and then I substitute values of S, values of M of S, which is just G of S, right? At the end of the day. So if omega is 0, so replace this with J omega. This value is 1 by J plus 1, whatever that comes out to, right? And then I substitute 1, you will end up with, 1 by 1, which is just 1. You would have 1 by J plus 1, 1 by 2J plus 1, and then all the way up to infinity, which would lead to 0. Right? So I take different values, and this would give me a complex number, which I can then represent it as some magnitude and some angle theta. Right? So each of this can be represented as some magnitude, some angle theta. And that is exactly what I plotted here. Magnitude is the length of the vector. Theta is the angle of the vector from the x-axis. Right?
So when you talked about phase margin on the Nyquist plot, is that the same as the phase margin on the Pody plots?
One and the same. Right? And I'm getting to that in a second. Right, so every single point that we have put here, we can substitute, get g of s values, and basically have the vector length and then the angle, so different values. So the first, second, 1/3, 1/4, and so on and so forth. Plot every single value and you get it. What do we do when we do Bode plot? We do the exact same thing. So how do we get a Bode plot? We have some magnitude of g of j omega. And then we have some angle of g of j omega. Okay? Typically, this would be a negative 180-degree axis. And then this would be our, so we would like to plot this in log as well. Sometimes 20 log. Right, so if the magnitude of this is 1, which would be the case where omega was 0, right? If the magnitude is 1, then the log of 1 will just be 0, there will be some value. And then at that point, whatever the angle comes out to be, you will plot that angle, let's say that's minus, so let's say the 0 degree, and that would be, let's say, minus 45 degrees or something. And you would take a lower frequency and then figure out what the values are, the different values that we have, right? How the curve looks like. And you would get some phase angle plot as well for it. It could go very well below 180 degree. In our case, it won't, because the system we took was stable to start with. But it could have this kind of plot too, for some kind of complex system. Right? So this is what we are gonna do in the Bode plot. So you take the different values of frequency omega going all the way from 0 to infinity, find out what the magnitude is, find out what the angle is. You have a separate magnitude plot, you have a separate angle plot. The Nyquist plot is just combining the magnitude and the angle into a vector form. All right, so in a single plot, you get all the information that you want. Here, you're just splitting it into two different plots. Okay. All right, so let's look at the corner case where it was at the boundary of stability and instability, okay, where it was at -1 plus j0. So if I look at the vector, okay, this vector, how will I represent that vector? What will be its magnitude? One, and the angle?
Minus 180.
Minus 180, same as plus 180. But we like to measure it on the other direction. So we have one angle minus 180 degree. So this is where our boundary of definition, the step between stability and instability is. If our curve is somehow able to collapse within this region, turn it a little bit around and collapse, it will be stable. If our curve goes a little bit outwards, it will end close to -1 plus j0 and it will become unstable. And the farther away from it we are, the more stable our system is. So if I had -1 plus j0 and I had a system that looked like this versus a system that looked like this. Okay? The second one is stable, more stable. Both of it are stable. This one is slightly less stable, but it's still stable though. Right? Why are we defining this as slightly less stable than this one? What could cause this to become unstable?
Then more phase.
What?
More phase.
More phase? Perfect. So the phase can come from multiple different ways. We just also looked at one example where our measurement is delayed in some way. Right? If our measurement is delayed, this gets pushed a little bit backwards. This curve also gets moved a little bit backwards. But there is a lot of angle between this -1 plus j0 before this vector, which has a magnitude of 1. Right? The vector with magnitude 1 is here for this. The vector with magnitude 1 is here for this one. Okay? This one turns just a little bit, can enclose -1 plus j0, but this one has to turn quite a lot before it starts to enclose -1 plus j0. So system can have significant amount of delays, and the first one will survive and be stable. Or as our motor keeps running, our resistor, inductors, J, B, all of those changes. Right? We saw last week how all of those parameters can change. So control system that we designed might have started out like this, our open loop transfer function, but our open loop transfer function will change over time as the motor heats up, core saturates, all of those. Right? So it can end up going to this location where it's much closer to -1 plus J0. But if we started with a controller that was already putting it here, as the motor parameter changes, it can push it around and make the system unstable. Right? So the degree, the way we measure this is how far this magnitude 1 vector is from the negative 180 plus J0. Right? This is called phase margin. So how far the magnitude of G of the vector representing magnitude of G of J omega equal to 1, how far the angle of that vector is from -180 degree. That is our measure of stability. The farther away, more stable our system is going to be. Right? And going back to our Bode plot, let's say our Bode plot look like this. And wherever the magnitude of the Bode plot is 0, because that's where the magnitude of G of J omega is 1. So log of 1 would be 0, right? This is equal to log of 1. Wherever the magnitude is 0, find out whatever the angle of the system is. This is going to be a phase margin. How far away it is from 180 degree. What does it mean if this is already below 180 degree?
Already unstable.
Unstable. If it's already below 180 degree, then it's unstable. What would it mean if it is the system stable? Quite stable, right? Because what the system is actually representing is somewhat of a, there could be one vector which has magnitude 1, another vector far out, right, which has a magnitude lesser than 1, but its angle is much greater, which is absolutely fine because it's still not enclosing -1 plus J0. Alright, so far out we can have phase shift greater than 180 degree and it should be fine, our system will survive. Because the idea is, if the signals are behind, what does the phase margin of 180 degree mean? If I give some signal input, let's say a sine wave, and then this transfer function does something and creates some other sine wave. If the sine wave is 180 degree phase shifted, that means this negative becomes a positive in effect, right? It's same as taking the signal and adding it to itself, and then going as output, and then coming back, adding it to itself, adding to itself, adding to itself. That's what instability is effectively occurring, right? But if that magnitude is collapsing a lot, right? If it's, let's say you start out with 1 volt and you get 1 volt, which is also phase shifted by 90 degree, then we are in quite a bit of trouble. But if we get a voltage, let's say 0.9, that's phase shifted by 180 degree, then we are okay. Because what is it? It's 1 plus 0.9 plus 0.8 plus 0.7 plus blah, blah, blah. This is going to converge. It's not going to go to infinity. Right? That's a converging signal. So the phase shift being greater than 180 degree is going to make it unstable only if the magnitude is also greater, 1 or greater than 1. Right? So if you had instead of 1, you had 1.1. Right? So whatever the signal is, so this, if it had a phase shift of 0 degree, if it had a phase shift of 180 degrees, this is what the signal would have looked like if you didn't have this negative. But since you are putting a negative, this ends up aligning with itself, keeps on adding. If you have a signal greater than magnitude 1, then it's add more and more faster, becomes more and more unstable. Right? So anything happening afterwards is fine. It is only the point here that matters. What if, is this a stable system?
Is there a name for the curve that you've been drawing that like either does or does not circle the like -1 point?
This one,
Yeah, is
it's just a Nyquist plot.
the curve for the transfer function have a name?
The curve for this curve, right?
It's just called a Nyquist plot.
This is called, as far as I know, this is just called the Nyquist plot, right? The Nyquist plot would be the whole G of J omega going all the way from plus or minus J infinity to the full circle as well. In our case, for systems of the order numerator less than order denominator, that semicircle part disappears, right? So including the semicircle part, the whole thing is the Nyquist plot.
Sure. If you have a system that's closed, open loop unstable, you can't make it stable with a purely proportional controller, correct? If it's just growing
If you have a closed loop unstable system, sorry, open loop unstable, like S minus 3 or something. Yeah, if it's a first order system, you should be able to stabilize it just with a Kp value. I don't know for a higher order system if that will be true.
You said if it encircles the -1 point, all you're doing is growing that.
If it was a single encirclement, right? If I have double pole, it will be a double encirclement. Right, so, oh, okay, nice. Oh, that's a good visualization. Yeah. So let's say, so we start off like this, that would be the case of a single pole, because it's just a single encirclement. And then of course you can scale it up and down. Case of a double pole, I think so. Yeah, you should be able to do that. Right, in this case too, you shrink all of this effectively, you should be able to make it stable. It should be.
But you said when you add the proportional gain, does that grow or shrink that curve?
Yep. Yeah, so if you scale it, so basically shrinking this, right? Putting our Kp value.
That's what it does, is it shrinks it, not grows it?
If it is. So let's say we chose a gain of Kp. 3. It's Kp. Oh, sorry, wait. This whole plot is not at all applicable if you had a pole on the RHS.
Sure.
Isn't that our first condition? Right? Our whole. So we said that when we had this plot, and then we went to our Nyquist domain. And to analyze the concept of phase margin and everything, we said there are no poles to start off with on the RHS plane, right? So our whole analysis itself will completely collapse if there is an RHS pole. Yeah, that's what I was wondering, because Kp higher would make it stable, but there the image as appears as if it's going to make it unstable.
So this whole analysis only applies for open loop stable systems?
Yep, that was the criterion 1. So the criterion 1 was open loop stable system, and the criterion 2 was the order of numerator less than order of denominator. Okay. Very good question. Any other questions? All right. Okay, so we have our system. So now let's go ahead and try to design our controller for a DC motor. So our DC motor transfer function model 1 by SL plus R. Right, this was just the MATLAB model that you all had. Some EMF, some voltage, and then this is our current. Scale it by kT becomes your torque, electromagnetic torque. Subtract your load torque, put it into 1 by Sj plus B, becomes your speed. Scale the speed by Ke, becomes your back EMF, and we complete the loop. So when we looked at the case of the driving example, we had our car, and then some PA controller. And this PA controller itself is one some gain value Kp, and then some integral gain Ki with an integral output, and then these two summed up together. Right? This is what is inside that box there. And what comes to it is going to be the error between our desired velocity, V desire, versus V actual, coming from a speedometer. So this is what we did, and we looked at the logic of what's going on here. If the difference between the desired speed and the actual speed is very large, then I want to proportionally apply a force on the gas pedal that is quite large. But as this error starts to reduce, I want to reduce the amount of force I put on the gas pedal, and that is being represented by this Kp block here, right? And the problem with the Kp block, what was the problem with Kp alone? Why did we put an integral controller? In our car driving model, why did we just model our brain with just a Kp controller? What was the reason for an integral controller? Yeah, Joe.
Because when we get to the correct velocity, the KP will go to 0, so it'll just stop applying the gas.
Perfect. So if V desired becomes V actual, then this error becomes 0, right? If this error is 0, then KP is not going to do anything. 0 times whatever gain you put, it could be very large, it would still be 0. But we know from experience that even if you reach the desired state, you still need to keep putting some pressure on the gas pedal because of friction. If there is no friction, then you don't need to do it. So because of friction, there needs to be still some kind of force applied. So the function that can get us that, where even after the error has gone to 0, it would still keep the output non-zero as an integral. If you integrate the area under this curve, even after this has gone to 0, right, the output can still be maintained at some value that would sustain the energy required to overcome the friction, right? And we can scale that with some k value so that our response can be modified as we want it to be. So we are going to do the same thing for a motor. We're going to put a PI controller there where we want the speed to be controlled. So why not just put a PI controller there? So whenever I put this PI, it's the same thing that I've drawn at the bottom. And I want the speed to be some reference value. And I'm going to look at what the current speed is coming from the motor. So this whole thing is the actual motor, right? This is not the control system or anything. This is the actual motor that we are modeling mathematically. But in a real world, this will all be the actual physical motor that you hold. The only variable you can control is the voltage. You can measure the current in the motor by putting some kind of current sensor. So this information is available to you. The speed again is available to you. You can put some kind of speed sensor, right? Some kind of encoder to get the speed signal as well. Speed and position signal, all of those are available to you. And the only thing you can control is your voltage. The torque is coming from some other external entity. Right? In case of an elevator, it's the number of people getting in case of the crane, it's the load that they are lifting. In case of a fan, it's the speed at which it's rotating and cutting through the wind. So that load torque is not typically under our control in a motor. In a generator, that's something we'll control. The voltage is not under our control. Right? Okay. So we have some reference speed. We put some PI controller, and we are going to have this transfer function, and we can figure out how to model this. But this is a little bit of a complicated transfer function because the order of this transfer function, if you look at it, well, we have order 1 here, combine that together, you get an order 2 transfer function, and then you close the whole loop. It gets a little bit more complicated, and there are a lot of in-between terms as well, right? What do we do with this towel? How do we eliminate the Z term, and so on and so forth? So what we're going to do is we're going to first model a reduced order system, and then try to compare it with what would have happened if we try to control this particular system that we have here, right? So let's start off with a very simple case. There I just say I don't want to control the speed starting right away. Let's say I just want to control the current in the motor. So how do we do that? So again, the transfer function for a current is 1 by SL plus R. The output of this would have been the current, and the input to the system would still be our voltage and our back EMF going into this, and the voltage is coming from here. And then we have our PI controller. And then this is my I reference, whatever current I want the motor to go to, and what the actual current is. Can everybody give me an application where I would want to control the current of a motor? Yep.
An EV,
What was it?
an electric vehicle.
EV, so traction application, right? Because the current is directly proportional to the torque. Whenever I say current control, it is basically the same as saying torque control. Right? If I control the current, I'm controlling the torque. And typically in any kind of motors at particularly low speeds, right, you would want to do torque control. As you go to higher speeds, you would want to push it to set to some particular speed and go from there. You would want to, when you're starting off, you want to have torque control. When you go to some particular speed, you want to have speed control, right? So there are applications that would require purely torque control on its own itself. But in our case, we'll extend this further to the speed control. But for now, let's start off with this current control. Okay, so let's write down the equations for the PI controller transfer function as well. But there is still the problem with the E term, right? That's kind of coming in between, which is not because all the system that we analyzed so far has this nice transfer function G of S, positive, negative. Like this is what we have analyzed and did all our Nyquist analysis and everything. It was a single input, single output system. we don't know how to handle multi-input single output system, right? Because there we have I as our input, E also as our input, which is quite problematic for us. So we need to reduce it to this form before we can do anything about it. But let's write down the system first. Can somebody tell me what the transfer function of the PA controller would be? What is the transfer function of a PA controller?
AP plus KI over S.
KP plus KI over S. KP plus KI over S. Because all I had there was some KP and then some KI integrated and then sum them up together. If I take the Laplace of KP, that's just KP. If I take the Laplace of KI and then integrator, KI times an integral d to some f of t dt, it is just going to be KI divided by S times f of S. Okay? So it's KP plus KI by S or KPS plus KI whole thing divided by S. Okay? So we have everything in place right now, but the only thing is eliminating this backgammon B. In control system, when we have this kind of system and we have this kind of thing coming in between, what would you typically call it as? A disturbance. Now, in the motor case, it's not a disturbance, it's the actual thing that makes the motor work. But for a control design, it's quite a bit of disturbance because we don't know how to handle this in a way that aligns with all the analysis we have done so far. So what we're going to do is ignore this term as if it doesn't exist and design a control system and then see that nothing really matters when certain constraints are laid on how the E varies. So let's go back to our real world example where again we had our car and we had some PI controller. We are looking at the actual reference speed and the actual, and we are doing some action on it. And somebody tell me some kind of disturbance that can come into picture.
The wind.
The wind would already be modeled into our system. Let's say that would be our, in our case of 1 by Sj plus B. Right, B is effectively the frictional component. And J would be our inertial component, which is if you are driving a truck, you know you need to put a lot of gas because the inertia is too large. And if you're driving a tiny car, you don't need to put that much pressure. That we know intuitively, we have modeled the system in our head, depending on whatever car we are sitting in. Some of the disturbance needs to be something external to the system that's already been modeled. Okay. Let's say you're driving on it. Sorry.
You get wind gusts though, right?
Wind gust, yeah, oh, perfect. That wouldn't be modeled as part of the system. Right? So you can have wind gust or some condition changes. You're driving on a flat road and suddenly the road starts to curve, or you start to get a slope, right? Or a mat is stuck in between the gas pedal. You need to put a little bit more gas so you can clear it. Right? All of those would be disturbance terms. But we know that when we learn to drive car, we don't encounter all of these disturbances. We just look at a very ideal case, learn, tune our PI values in our head. And afterwards, as long as there is some constraints on these disturbances, we can still comfortably drive pretty safely without becoming unstable. Can somebody tell me what kind of constraints would be put on this disturbance so that whatever system we designed before without the disturbance would still remain stable once we encounter these disturbances too? Let's take a case of a road which was going straight itself, and then the road has a bend. Right? All of you know that you can get through that bend as long as you're driving. Right? When will you get into a place where you cannot control and keep your car stable? What must be the characteristic of that bend? Yep, James.
If there's like ice or something, like no friction.
Ice, all right. What is the underlying characteristic of that?
Does it have to do with like your control loop not saturating?
Nothing to do with saturation. Or how do you explain saturation in the case of the driving? There is
Like using all of your control input, the extent of your control inputs?
Yeah, let's assume that your wheel can do 180 and farther and farther. Let's assume just the pure linear system alone, right? In this PI case, we don't have any kind of saturation, right? The output of the gas pedal, let's assume, can go as much as possible. What would be the constraint on the curve of the road itself that would make your system unstable? If it curves too fast, you won't be able to control. No matter how good a driver you are, there will be some breaking point where if the road curves a lot, your system would become unstable, right? So you can tune your system to be stable as long as the external disturbance that is changing is not changing at a rate faster than what your brain can respond. Whatever control system you have designed, the bandwidth of the control system, right? So the term that we would use, bandwidth. If you're driving on a straight road and you encounter a sudden curve or when you encounter an ice, the problem is your brain and your eyes haven't processed the signal at a fast enough rate that your PI controller values effectively in your brain, whatever those equivalent values are, those bandwidth determined by those values is not large enough to account for a disturbance that's changing too fast. Right? If the curve in the road was looking like this and you are driving and you can probably account for it. But if it looked like this very fast, before you see the next curve and process the data and create a signal to it, your system is already good. So here you would try to correct and come inside, but by the time if you're here on the road, you would go farther out from the road, right? So if your way at which the disturbance is interacting with your system happens to be much faster than the bandwidth which you have designed your controller and the speed at which your car itself can respond, then you become into unstable system. Or even when you're turning on a highway, if you do too fast a turn, right, your car becomes unstable because the disturbance, the curve that's coming out ends up being much higher than what your car can handle. Your car can topple over. So let's come back to this case where I'm saying the EMF is a disturbance and I can ignore the disturbance. What constraint should I put on the EMF before I can start ignoring it in my controller design? What was the constraint here in the case of the car? That whatever external situation happens should not happen at a rate faster than my car can respond or my controller bandwidth can respond. Okay, what would be the constraint for the EMF? Okay.
Does your controller bandwidth have to be faster than your fundamental frequency of your motor?
Right, perfect. So the rate at which our PI controller bandwidth must be greater than the rate at which our disturbance is changing or rate at which our EMF is changing. Right? And also you want the EMF to be changing slower than the car, in this case the car can respond, or in this case the electrical system can respond. Is that constraint satisfied in our motor? That the EMF should change slower than the electrical system can respond. How is it satisfied? That was the last question of homework 6. Okay. It's basically the time constant of a mechanical system and the electrical system. Because what is dictating the EMF? EMF is Ke times omega. And what is dictating our omega? That is Kt divided by Sj plus B. With current coming in, I put the Kt inside because torque is Kt times I. I'm leaving the load torque for now. And then we get omega. Right? So the rate at which our EMF is going to change for any changes in the current is going to be dictated by our time constant of a mechanical system. But the rate at which our electrical system is going to be determined by the time constant of our electrical system, L by R versus J by B. And as you all saw on the homework, L by R was 4 milliseconds in the homework, I think. J by B, I think, was 1 second or 0.4 seconds or something. Right? So at least the order of 100 to 1000 times larger. So it's absolutely fine ignoring this EMF because we know that for a change in the current, the EMF will change so slowly that our control system will be able to adapt to it, which is no problem at all. Same as how the road is changing quite slowly, we can quite easily process it and become stable and drive comfortably. If it changes too fast, we run into trouble. But that alone is not sufficient. Whatever controller we design, that also needs to act much faster than the rate at which our speed is going to be changing. Right? So there are two constraints. The first constraint is automatically satisfied for all practical motor. Second constraint is on the controller that we are designing, which we need to make sure that this happens. Right? When we finish our full control system, we need to ensure that the bandwidth of the system is much, much larger than any rate at which the EMF can change. If it doesn't, then our whole assumption of ignoring this EMF is completely faulty. Right? Anybody have any questions? Okay, so with that assumption, let's go ahead and design. So our G of S transfer function, can somebody give me the G of S transfer function in this case that I've drawn? For this one, what will be the full transfer function? Just the open loop transfer function. What will be G of S? It's a very simple question. The addition sign is blocked. There is nothing here. So what is the G of S?
Are we just assuming the mechanical system?
Yeah, just could you repeat that? Sorry.
Since the mechanical system has a higher time constant, we're only solving for the mechanical system since it responds with.
No, since the mechanical system has higher time constant, we are only solving for the electrical system now. The mechanical system is completely out of the picture because you're only trying to control the current right now, right? And we said the EMF is no longer playing a role in this controller design because it's just a disturbance that's varying too slowly, so we can just ignore it. So the question is, what is this open loop transfer function for the system now?
Just multiply the two, right?
So multiply the two, perfect. So it's just the KPI controller transfer function, this one, KPS plus KI divided by S, and the electrical system transfer function 1 by SL plus R. Now, we're going to do a couple of things. Let's say at some frequency, let me call it omega C, crossover frequency. Yeah. Let's say at some frequency, the magnitude of this transfer function equal to 1. What should be the angle of G of j omega for this to be stable? What?
Less than 180.
Less than 180, perfect. So less than negative 180, right? Because the angle we look at is this side, this angle here. So less than negative 180. So as long as it is some positive value greater than the negative 180. So if it's negative 140, our system is stable. If it's negative 177, it's stable. Negative 179, it's stable. But if it gets to negative 180, we are at the boundary of stability and instability. If it goes above negative 180, it becomes totally unstable, right? So we want to have some kind of phase margin to our system. And as long as the phase margin value is positive, our system is going to be stable, right? This omega C is what is I deleted that crossover frequency that we get to choose in our system. We can put it wherever we want at the chosen frequency where the magnitude is equal to 1. We better ensure that the angle of this transfer function is not getting close to negative 180 degree, right? So can somebody tell me what the expression for the magnitude of that transfer function there would be for G of j omega? It's equal to 1, but substitute that, so let me do Kp j omega, right, plus Ki. So I'm substituting S with j omega at all points divided by j omega times 1 by j omega L plus R. If I take the magnitude of this, what will it be? What will be the magnitude of this term? Let's do the simple one first. What will be the magnitude of the 1 by j omega L plus R? So the magnitude of this is going to be 1 by square root of plus R square. This is again the same complex number. So square root of Kp omega square plus Ki square. What will be the magnitude of this? What will be the magnitude of j omega if I take the magnitude for j omega?
Just omega.
Omega, thank you. Again, it's just a complex number, right? So just take the square root of real square plus the imaginary square. Okay. And this must be equal to 1. Can I solve this for KPKI? No, right, we have two variables, one equation. Where do I get the other equation?
Taking the phase.
Perfect, taking the phase, so I only have this other equation here. So let me take the angle of g of j omega at the crossover frequency omega c. What will be the angle of this? Just the tan inverse of the imaginary divided by the real for any complex number. Tan inverse of omega kp divided by ki. Angle for this? Is it same tan inverse omega L by r? No. What am I missing?
Negative.
Negative sign. Negative tan inverse omega L by r. And the negative sign just comes from multiplying by negative j omega L plus r, negative j omega L plus r. Right? So that's where the negative comes from. This is where the magnitude component comes from when you do the complex conjugate multiplication. Okay. And the angle of this itself is going to be, if it was j omega on the numerator, that would be tan inverse of j omega, tan inverse omega divided by 0, imaginary by real. So it will be 90 degrees. Since it's in the denominator, it will become negative highlighted. Since we are doing angles, let me keep it in angles, equal to negative 90 degree. And this must be equal to negative 180 degree plus whatever phase margin we choose. Chosen value, right? So our omega c is to be chosen by us. And then a phase margin is to be chosen. Now can I solve this equation? We have everything, right? It's a nonlinear equation. So you can't put it in some kind of nice matrix form and invert it, unfortunately, but you do need to figure out Kp in terms of K or K in terms of Kp from one of the two equations and substitute into the other equation and solve it, right? So that's what's done in the manual on the SciML website that you can follow if you want. And that's what you'll be doing for the homework 7. Okay. Everybody clear about how to pick Kp, K values for a controller? Yeah, okay.
Why is this G of S and not C of S? Don't you have a controller in there, so wouldn't that be the closed loop transfer function?
No. So the Nyquist stability criterion that we had was analyzing the phase margin. All of those was defined for the open loop transfer function, which in turn dictates the stability of the closed loop transfer function.
But
Right.
you labeled this G of S, so that would be the open loop transfer function?
By open loop transfer function will be just the part before I close it.
Sure.
Right? So this whole thing is the open loop transfer function. If I didn't have this connection.
But you include the controller itself in
Yeah, but
the,
it's including the controller as well. So when I had G of S, it was a combination of planned transfer function and the controller transfer function. Any other questions? Yep, sorry, John.
I'm just confused where the minus 90 degrees came from.
Minus 90. Oh, comes from this angle of j omega
Oh, okay,
on the
yeah, got
denominator.
it, thank you.
And so this again take complex conjugate, negative j omega, negative j becomes positive 1, you get omega square. And then you have omega cancels. So the magnitude is just omega, and the angle is minus j, which is negative 90 degree. Any questions? Okay. So now that we have designed our current controller, we can control our current. So what do we mean by we can control the current? If I were to give some kind of step reference or not any kind of reference, right? So let's say I make my current go like this. And then if I have the PI controller, then R1 by SL plus R. And then of course in the real world you would have the EMF disturbance, right? But as long as the disturbance isn't varying too much, then what a current response would look like is if my bandwidth of this controller is pretty large, then the current would look exactly like the reference that I had. Right? It could be this response, or it could end up looking like this. Right? So we have multiple options as to what the response can look like. Right? So can somebody tell me what must I change for the response to go from this to this or this to this? Well, you'll have to change the KPK values, that's obvious. But within my control parameters, what do I change? stability, perfect. So basically choosing the phase margin, right? If my phase margin becomes very low, if I go very close to 180 degree, negative 180 degree, if I go to negative 180 degree, that will be the boundary of stability and instability, which I know is going to create this response, right? Which we have bounded input, bounded output, but non-convergent output, right? Bounded but non-convergent. If it is stable, the more and more stable the system gets, it goes like this, and then it goes like this, and then it becomes more and more overdamped, right? So if I choose my phase margin to be very close to zero, or if I lie very close to negative 180 degree, then my response is going to be quite oscillatory. If I make my phase margin go to very close to 90 degree, or this is farther away from the real axis, very close to the j omega axis, then we get to an extremely overdamped case. Which one would I prefer?
Somewhere in the middle, like 45 or so.
Why?
Just you're not over damped or under damped.
Well, what is special about that 45 degree?
It's critically damped ideally, like in an ideal case.
Right? Is 45 degree the critically damped case?
I don't remember.
Right? So the concept of the critically damped, all of those would come in the second order transfer function without the zero on the numerator. Right? So in our case, the transfer function would end up being a little bit more complicated with zeros on the numerator as well. But the values you would choose can be any values. It's totally up to you as a designer. But we definitely know it needs to be between 0 and 90 degree. Typically for our motor control applications, for speed control and stuff, we would try to put it around 60 degrees if you don't do online parameter estimation. Right? Why would I want to put it around 60 degrees if I don't do online parameter estimation? Because even if my motor parameters changes and my motor, the Nyquist plot that I drew very closer to negative 1 plus J0, there is enough phase margin that my system can still remain stable. Right? If you are doing online parameter estimation, you have a good model of your system, you can push this value much lower, even to 45 degree or to 30 degree, which would make it go from overdamped case to this kind of more oscillatory behavior. What do we get by going to this more oscillatory behavior?
Faster response time.
Faster response time, right? Because as soon as you apply the step in your pedal, you want the car to get to your actual desired speed as fast as possible in case of, let's say, electric vehicle. If you have it overdamped, if you have the phase margin very close to 90 degrees, it's going to take quite a long time to get to the final steady state value. It's going to have a very lagged response. If you want to have a very fast response, you would make your phase margin very small. But then there comes a problem that even the slight changes in the parameter could destabilize your system. So if you want a fast response, you better have a good estimate of your model as system as well. If you have a very bad estimate, you have to settle down with a very slower response so that your system can remain stable for a wide operating range. Right? So in the remaining 5 minutes, let's design the speed controller as well. So now that I've designed the current controller, so this is my current control loop with my PI, with some current reference coming in, with current feedback goes into the PI, and then my back EMF term, which was a disturbance, and then 1 by SL plus R. This was giving me my current output actual, and this is going to go into KT value, become electromagnetic torque, subtract the load torque, 1 by J plus B. And what I'm going to now do is put another PI controller. Omega reference, omega FPK. And the output of this PI controller is going to be the current reference that I'm going to be feeding into our previously designed current controller. Yep, Ben.
Oh, where does the 90-degree bound on phase margin come from?
90-degree bound of phase margin. So that will come from the fact that our PI controller has only a single zero. Right? If you had, let's say you put SKP plus KI the whole square, then you can push it to negative 180 degree further out. Right? It's just from the single zero that we are kind of putting on the numerator. Okay. Any other questions? Okay, so Yeah, so we are going to put another PI controller at the output coming from our speed, desired speed reference. We look at the actual speed, put it to PI controller, and we're going to connect it to our already designed control system, which requires some current reference to go into this. So this is one way of doing it, or the alternative was the first method that I do, which was take a PI controller, and then we have our omega reference, omega FPK. Both of it is okay. One is preferred over the other. And this goes into our full motor model, the complicated, the big one, which I raised. And then omega comes in the output. So this is also fine. Either way we can do it. But there is a big advantage with doing this. Let's say that this system that I've designed has a bandwidth, or basically the crossover frequency omega, that is very large. Then what does that, in the control system term, what can I equivalently model it as? So in case of, let's say you have your, a movie is going on the screen, right? You have 60 frames per second. It is a discrete entity that's happening at certain instance of time, but your eye looks at it as if it's continuously happening. So in your case, what would be the transfer function between the movie theater screen to your eye? How will you model the transfer function? It's just a unity gain, right? Whatever is happening on the screen, you're instantly capturing it in your eye, right? Because there is nothing being lost there, because this is happening at too fast, your eye cannot just process it. So as well as there is a continuous picture coming and you're just seeing it continuously on the same time. Now, if my PI controller, this whole system is operating very, very fast, right? If I apply a step and then the system reaches that step quite fast, such that the outer speed controller does not even see that happen, because the outer speed system is happening at a much, much slower time rate. This whole thing just can be modeled as a equivalently as a unity gain block. As far as my outer controllers matters, i.e. actual, right? Because what does it mean? Because all of these fluctuations going on in an electrical system, that is not going to affect a mechanical system at all. Because the mechanical time constant is very large, J by B. So if I apply, that's the same thing that we use when we did parameter estimation, right? We applied a tiny pulse and shut off the whole system so that the mechanical system didn't have time to react, because the mechanical system is going to react very slowly, but an electrical system had time to react and reach steady state, and we could get the electrical parameters right away. So the same thing is going to happen in this case as well. If we design our controller for our inner current controller to operate in a very fast manner, then the current is going to appear as if whatever we asked from the current controller is instantaneously given, because the speed controller cannot see it, because it's operating at a much, much slower time scale. Right? So very clear on this part. So now, what does this whole system now look like? Back again to our original system, we have KPS plus KI divided by S. Now some of the KPK values, unity gain, this is KT. So let's have the KT here for now. Again, I have this torque coming into our picture. Can I do something about the torque? Can I call it a disturbance? Well, it is disturbing me, so I'm going to call it a disturbance. But I need to put constraints on this disturbance. What is the constraint?
The bandwidth of the system has to be much greater than the rate of change of that disturbance.
Perfect. So if I have this load torque, and let's say this load torque is changing like a step, it can change as long as it doesn't change too fast. Right? If the frequency of this gets too large, it gets larger than the crossover frequency that I choose for my speed controller, then the speed controller cannot anticipate those changes and address it, right? But if it changes slow enough, then what a speed controller can do is still kind of match up with the torque by generating a counter electromagnetic torque, right? So the torque should not change faster than whatever bandwidth I'm going to be choosing for my PA controller here. As long as I satisfy that constraint, this again can be modeled as a disturbance, and I can ignore it, and my PA controller will take care of it without any issues. 1 by Sj plus B omega ref, omega feedback, and that's it. Can you design the controller for this? Okay, for exactly same method that we did before, instead of j omega, this would be j plus b, and there is a kt factor added onto it. That's about it. Nothing else changes. So this will be j, this will be b, this will become kt, this will be j, this will be b, and that's it. Rest all remains the same. Again, you can choose a phase margin of your choice. If you want to be more conservative, then stable, go closer to 90. If you want to take a little bit of risk, get this phase margin closer to 0, and that's about it. What would be the limitation on the crossover frequency, the omega c that I choose? Is there any limitation, or can I choose any omega c value as well? Yeah, really.
Well, yeah, now you have to make sure it's gonna be higher than the frequency of the torque, low torque.
Perfect. So excellent answer. So the omega c for the mechanical system has to be greater than the omega at which the load torque is changing. Do I have upper bound as well? It definitely has to be greater, but is there a limit on how large it can be? Yep, John.
It has to be slower than the electrical control system.
Okay, that was the first condition. Omega ci. So whatever crossover frequency that I choose for the electrical control system, okay, so let me call this omega ci. Whatever frequency I choose for the PI controller for the omega c mechanical must be lesser than our electrical control system bandwidth. If it is not, what assumption are we violating? When we designed the electrical control system, we made a very big assumption that led to the simplified model, which will get violated. Which assumption would get violated if my mechanical bandwidth becomes much larger than my electrical bandwidth? Yep, Chris.
Back EMF is irrelevant.
Back EMF irrelevant. So when I disappear this term out as a disturbance, I said that the EMF is not varying as fast as the electrical system. But if I design a control system, mechanical control system that is going to operate much faster than the electrical control system, this assumption is no longer true. Then my system becomes complicated. All the design that I've done for my inner control system is completely wrong. Just because the mechanical time constant is low, that does not mean once we put a controller, the time constant, response time also must be slow. I can design a controller that has a crazy large KP value such that it responds quite fastly in mechanical term. We can even design it so that it responds faster there compared to the inner current loop, right? But that would defeat the whole purpose of doing this. So let me take just 2 more minutes. Those of you have to leave, that's absolutely fine. Let me extend this just a little bit further. Is there a limit on omega ci? So clearly the upper limit is omega ci. So for omega ci, the lower limit is omega m. Omega crossover of the mechanical system that we choose. Is there an upper limit?
Is it the properties of the electrical system itself, how fast they can change?
Perfect. Which would be
Based off your inverter switching
perfect.
characteristics.
Inverter switching frequency. FSW. So if you have an inverter, which we looked at in the third lecture, right, and this is creating some switching output voltages, you cannot expect the current to be created faster than what the inverter can switch and create the current in. Right? At the end of the day, when you resolve it into Fourier components, it has to be multiple of the switching frequency terms. You cannot create some other random frequency which is much higher than what this is. So that would be the Nyquist limit, which would be the very upper bound, which would say that at the maximum it can be half of the switching frequency. Alright, so if you're switching at 10 kilohertz, your current controller bandwidth cannot be greater than 5 kilohertz. Afterwards, you'll get anti-aliasing and the control system could start to act quite crazy. The way we would choose these values are typically our omega ci would be about 1/10 of our switching frequency, and our mechanical bandwidth would be 1/10 of the electrical bandwidth. Right? So let me extend this a little bit further. What do I do if I want to control the position of the motor instead? Someone else? Since Isaiah has experience doing this, I'm not going to ask him. Anyone else? How will I model this is the omega of the motor. How will I model the system angle? If I know the omega of the motor, how will I get the angle of the motor, rotor angle of the motor? Just an integral. So if you integrate the omega, you get theta, because omega itself by definition would be theta by dt. Right? Once I know theta, how do I control this theta? I control the motor because the camera that we have right there, that is basically controlling the angle of the motor. Right? You could typically have a DC motor, it will be a real DC motor in that case, and you're basically controlling the angle. So how do you control the angle? You can just cascade one more PI controller. So close this loop, theta reference, theta feedback, right? And you get the error. This error is going to go to PI controller, and that is going to control the speed. This error is going to control the PI controller, that's going to control the current, and that in turn is going to control the whole thing. You do not have independent control in this. You can't control both theta and omega. In the transient, you can shape how the omega looks like, but not in the steady state, right? Do I need a proportional controller? Sorry, do I need an integral controller if I'm trying to control the theta of the motor? It's a little bit of a complicated question, but with that we are done. Yep.
You want to answer that question?
Yep.
Like if there's like any disturbance that could affect the position, you might want like an integral term or something like that.
Right, perfect. There is no disturbance. In the case of the camera right there. Right, because once the theta reference reaches the theta feedback, the error is zero. You do not want any speed to be there in the motor once the error goes to zero in case of position control. So in those cases, you can just do with a position controller, P controller, but in case of disturbances, you would need a integral controller as well. With that, we are done. We will, in the homework, I've asked the question about the steady state value for which you need to use the final value theorem. So if you're not familiar with it, we can meet during TRs. Otherwise, I'll explain it on Friday. But if you have questions on it.
We're just go to act one.